Let's start with problem number 1. A gas occupies 100 ml at 150 kilopascals. Find its volume at 200 kilopascals. Let's first identify the variables. 100 ml is the volume 1 and 150 kilopascal is the pressure 1 and 200 kilopascal is the pressure 2, and we are asked for the volume. And we all know that this relationship is the Boyle's law. And Boyle's law, that is P1 V1 equals P2 multiplied to V2. Now, what if, for example, you forgot the formula of the Boyle's law? We only have to recall one equation, which is P1 V1 over T1, that is the combined gas law, equals P2 V2 over T2. Since we're only talking about P1, V1, P2, and V2, the temperature is constant, so we could cross this out. And therefore, this is the formula. P1 will be 150 kilopascals. Volume 1 is 100 ml. P2 is 200 kilopascals. And V2 is the unknown. Solving now for V2, that is 150 multiplied to 100 over 200. Simplifying, this one will become 2, 150 and divided by 2, and then therefore, we have 75. Therefore, the volume 2 here is letter B, 75 ml. Next, problem number 2. A certain gas was confined at a pressure of 40 atm with an initial temperature of 77 degrees Celsius. What will be the new pressure if the temperature was made at 427 degrees Celsius? So we have here the given 40 atm, that is the pressure 1. Next, we have here the 77 degrees Celsius, that is the temperature 1. Next, we have 427 degrees Celsius, that is the temperature 2. And for the pressure 2, that is the unknown. Suppose that we forgot the formula of Gay-Lussac's law. We have this general formula for the gas loss, P1 V1 over T1 equals to P2 V2 over T2. And we all know that the volume here is constant, so we could erase this and we could erase this. Therefore, the formula is P1 over T1 equals P2 over T2. Substituting now our values, the pressure 1 here is 40 atm over the temperature 1, which is at 77 degrees Celsius. Now take note, we have to work by Kelvin. So 77 plus 273 Kelvin, 350 Kelvin. So our temperature 1 here is 350 Kelvin. And pressure 2, that is the unknown. And for temperature 2, still we must add 273. So plus 273, 700 Kelvin. Therefore, we have here 700 Kelvin. Solving now for P2, that is 40 multiplied to 700 over 350. This one will be cancelled. Therefore, this is 2, and 2 times 40 is 80. And then we have the unit, which is 80 atm. Therefore, the answer here is letter C. Next, for problem number 3, a gas occupies a volume of 2 liters and a pressure of 20 atm. If the pressure is tripled and the original temperature is halved, what is the new volume will it occupy? Let's first identify the variables. We have here the volume 1, which is 2 liters, pressure 1, which is 20 atm, And if the pressure is tripled, so therefore the pressure is tripled, we have here 60 atm, and the original temperature is halved. So meaning to say, we have our T1, the original still the T1, and for the T2, the original temperature is halved. So therefore, 1/2 of T1. And then we are asked for the what is the new volume. Writing now our general formula, which is P1 V1 over T1 equals P2 V2 over T2. Writing now our solution, P1 here we have 20 atm multiplied to the V1, which is 2 liters, equals the value of our T1, still that's T1, and for the P2, that is 60 atm, and for the V2, that is actually the unknown, and for the T2, that is 1/2 of the T1. Solving now for V2, that is 20 multiplied to 2 multiplied to 1/2 of T1 divided by T1 multiplied to 60. Simplifying now, we have 2 and 1/2 here. This will be cancelled. The T1 from the numerator and the T1 from the denominator will be cancelled. And then 20 and 60, this one divided by 1, 60 divided by 20 is 3. Therefore, we have here 1/3. And 1/3 is 0.33. Therefore, letter A is the answer. Next problem. 30 liters of gas X is confined in a container in a pressure of 2 atm at 100 Kelvin. If the pressure is increased by 4 atm and the temperature is increased to 200 Kelvin, what is the mass of the gas if the density is 0.01 grams per liter? First thing that we need to do is to identify the given. So we have here the volume 1, we have 30 liters, and then we have the pressure 1, which is 2 atm, and the temperature 1 is 100 Kelvin. Next, the V2, that's actually the unknown, and then we have the P2. So if the pressure is increased by 4 atm, take note of this word by. So therefore, we have here 2 plus 4 equals 6 atm, not 4 atm. And then for the temperature, that is increased to 200. Writing now our general formula, we have here P1 V1 over T1 equals P2 V2 over T2. Solving now for P1, that is 2 atm, and the V1 here is 30, and the temperature is 100 Kelvin. And for the P2, we have 6 atm, and for the V2, that is the unknown, and for the T2, we have 200. Solving now for V2, that is 2 multiplied to 30 multiplied to 200 over 100 multiplied to 6, and then we have now the V2. Then simplifying, we have here 200 and 100. This one is 2, 30 and 6. This one is 5 and this one is 1. So 2 times 5 times 2, that is 20. And since the unit here is liters, that is 20 liters for the V2. However, we are not yet done since we are asked for the mass of the gas, and we are given here with density. So this one can be interpreted as 0.01 grams equals to 1 liter. So solving now, we have 20 liters multiplied to 1 liter and then 0.01 grams, and then therefore 20 multiplied to 0.01, that is letter B, 0.2. For question number 5, how many grams of chlorine gas can be stored in a 10-liter container at 24,900 kilopascals and 27 degrees Celsius? Use R as 8.3 liter kilopascals per mole Kelvin and chlorine as 35 atomic mass unit. Now, obviously, this problem, it involves this ideal gas law. And the formula for the ideal gas law is PV equals to nRT. Now, if we're going to check for the variables, we have here the pressure, the volume, the value of R, and the value of T. And since we are looking for the grams, therefore, we can conclude that we need to find first the number of moles. Let's do now our solution. The value of P here is 24,900 kilopascals. Next, the value of that volume, we have 10 liter. And the value of N is unknown. The value R here is 8.3. We have liter kilopascals over mole Kelvin. And take note for the value of temperature, we have 27 degrees Celsius. But we cannot use this 27 degrees Celsius, but rather we have to add 273. And therefore that is 300 Kelvin. This one will be represented as 300 Kelvin. Solving now for the value of N, that is 24,900 multiplied to 10 over 8.3 multiplied to 300. Take note that the overall unit for this will be mole. Solving now, we can see that 24,900 divided by 8.3. So we must be careful with our decimal. So we have here 8.3. So move this and then add another 0. And then 249 divided by 83. So we have here 3 multiplied to 8.3. That's 249. And therefore we have 3,000. So this one, we have 1 and then we have 3,000. Rewriting my solution, 3,000 multiplied to 10 over 300. 1,000 divided by 300, that is 10. And therefore 10 times 10, we have 100 moles. And that is the value for the N. But it's not yet done. We have to find for the chlorine gas. And chlorine gas, remember, chlorine is a diatomic molecule. Just to recall your diatomic molecules, these are represented as Hankel brief. And chlorine is one of them. So, that is, for the chlorine, we have 35 times 2, we have 70 grams per mole. That is for your Cl2. And since solving now, we have 100 moles of chlorine times, since we have here 70 grams per mole, I will write here my 70 grams on the top, 1 mole at the bottom, then therefore cancel, then cancel 100 multiplied to 70, and that is 7,000 grams. So therefore, the answer here is letter B.